So Professor Manuel Roveri received the PhD degree in computer engineering from the Politecnico di Milano, Italy, and the MS in computer science from the University of Illinois at Chicago. He has been visiting researcher at Imperial College London, UK. Currently, he is an associate professor at Dipartimento di Elettronica, Informazione e Bioingegneria of the Politecnico di Milano, in Italy, Milan. Since 2018, Professor Roveri is a senior member of IEEE and is an associate editor of the IEEE Transactions on Artificial Intelligence, of the IEEE Transaction on Emergent Topics in Computational Intelligence, of the IEEE Computational Intelligence Magazine, and of the Elsevier Neural Network Journal. Professor Roveri was associate editor of the IEEE Transaction Neural Networks and Learning System from 2013-2020, and guest editor of several special issues. Current research activity addressed embedded and edge AI, learning in presence of concept drift, and intelligent embedded and cyber physical systems. Professor Roveri is a senior member of IEEE and served as a chair and member in several IEEE committees. He holds one patent, has published more than 110 papers in international journals and conference proceedings. He is recipient of the 2018 IEEE Computational Intelligence Magazine Outstanding Paper Awards and of the 2016 IEEE Computational Intelligence Society Outstanding Transactions. Please, the floor is yours.
Thank you, Danilo. At first, good morning and good afternoon, everybody. Let me thank the organizers for the kind invitation, and let me thank the speakers for the very, very nice talks. It's a great pleasure for me to be here. This slide details my short video. I will skip most of them. I just want to highlight two main points. My email, which is name.surname@polyme.it. If you have questions or comments or feedbacks about my presentation, the presentation that I'm going to deliver, please send me an email in addition to the question that you can do at the end. The second point I want to highlight is the fact that in spring 2023, my university will deliver a brand new course on hardware architectures for embedded and edge AI, exactly on the topics of tinyML, on-device learning, distributed and federated learning. It's an honor for me to be the lecturer of this course, but in particular, the presence of this course shows the interest of my university, both from the research and from the teaching interest in the field of tinyML. A big thank also to my research team. It's a great pleasure to be the coordinator of such a group of brilliant researchers. But let me start my presentation going back to the title, which is on-device learning the next big thing in tinyML, which is obviously a provocative question that deserves obviously a provocative answer. And the answer is no. But let me rephrase this question as follows. Is on-device learning the big thing in tinyML? The answer is absolutely yes. And let me comment this answer by means of two examples. The first example refers to a news that appeared some years ago in 2016 on IEEE Spectrum, which is the magazine of IEEE. And this news describes a very simple but effective things, which has been carried out by a research team from University of Washington, US. We all know that the face recognition algorithms are able to provide very, very high recognition abilities, 99.5, 99.6. But what they did, the activity carried out by this research team was very simple. What they did is the fact they moved from the lab, so the analysis on benchmarks and data set, they moved from the lab to the real world, these face recognition algorithms. They emulated the real world by considering a very, very large data set with the different poses of people, different exposures, different expressions, different ages. And what they discovered is the fact that the classification accuracy, so the recognition accuracy of these algorithms significantly dropped from 99 point something to 66, from 99 point something to 50, and from 99 point something to 30, the first three algorithms. And the reason of this huge drop in accuracy is associated to the fact that when we move machine learning algorithms, deep learning algorithms from the lab to the real world, we have to deal with the environment and the system. So we cannot skip them in our analysis. And let me move to a second example that refers to a rock collapse forecasting system based on tinyML. We designed, developed, and deployed it in northern Italy and in Switzerland. The aim of this system is to acquire macroacoustic emissions which are coming from the rock face, which are possible forerunners of the rock collapse. So we acquire them by means of a MEMS accelerometer, MEMS accelerometer. We have also a strain gauge measuring the enlargement of the macro fractures. And this system must be completely autonomous in the sense that it does not have a direct permanent connection to the cloud or to a control room, because the communication here is very complex and very energy consuming. So the system itself must recognize the potentially critical situations and open the communication channel only when needed. Let me show you a brief video about the deployment of the system. Here you see this metallic case that embed the MEMS accelerometer. Here we are acquiring 3-axial accelerometer, which are sampled at 2 kHz. Here we have the strain gauge. And this is the San Martin Mount in northern Italy. And this is the Como Lake and the beautiful town of Lecco in northern Italy. This example is particularly relevant for the purposes of this topic for 3 main reasons. The first one is the fact that this system was the first example of a rock collapse forecasting system based on MEMS accelerometer. So we didn't have data to train our model before the deployment. So we had to deploy the system, we had to acquire data locally, and we had to learn the models, the machine learnings directly on the device. So perfectly in line with the purposes of on-device learning. The second example refers to the fact that the environment has an effect on the measurements. And if you see here, the strain gauge, which is measuring this, the enlargement of this macrofracture, this strain gauge is a metallic pipe that enlarges during the day and shrinks during the night due to the heating. So if we would analyze just the data coming from this strain gauge, we will have daily false alarms. This means that we have to understand, we have to learn the relationship between the heat and the strain gauge. So this means that we have to integrate the strain gauge with the temperature sensors, and we have to learn the relationship between the strain gauge and the temperature sensors directly on the device, so on-device learning. And the reason number 3 refers to the fact that this system, as you can see, has been deployed in summer. But then we passed from summer to autumn and then to winter, and the rock phase behaved completely different. So we had to continuously acquire data and then train our model such that it is able to track the evolution of the rock phase over time. So on-device learning is the big thing in tinyML, because tinyML is the so-called always-on machine learning. So we have sensors which are able to acquire data. We have a preprocessing phase that generates the input of our machine and deep learning model for the inference phase, model for classification, regression, or prediction. And then the output is then passed to the post-processing phase to make decision or activate reactions. Obviously through the actuators. But as I said, we might have changes which are present in the environment. We might have a periodicity or seasonality effect. We pass from summer to winter and so on and so forth. We could have a change in the user's interest or in the user's behavior. Like, for example, if we have a smart plug which is endowed with the speech command recognition, we might want to add a new command, or we would like to add, maybe to adapt the speech command recognition system to our accent, for example. The third type of change that we have to face is the fact that we might have false malfunctionings affecting the hardware, the sensors, and the actuators. Like, for example, having just some dust covering the lens of our camera. And last but not least, we have aging effects or thermal drift affecting our sensors. As I mentioned, the case of the strain gauge, which is heavily affected by the temperature. These events perturb the data, so changes the statistical distribution of the input data. This means that the probability density function generating the data, so characterizing the input X, changes over time. And this means that the model that we previously trained becomes obsolete. And if the model becomes obsolete, this means that the subsequent decisions that we can make are wrong or potentially catastrophic, because the perturbed, incorrect, or missing data heavily affect subsequent preprocessing and post-processing phases. How can we deal with this issue? We have to address this problem from two different perspectives in an integrated way. We have to design algorithms which are able to support the learning in presence of concept drift, where concept drift has anticipated in the previous talks. Concept drift refers to a change in the statistical distribution characterizing the data. So we have to design algorithms which are able to deal with concept drift. But then we have to take into account that these algorithms must operate in devices which are technologically constrained in terms of memory, computation, and energy. So let's start with the first issue, learning in presence of concept drift. This is a quite active and wide research area whose goal is to define machine and deep learning algorithms which are able to weaken the stationarity hypothesis, where the stationarity hypothesis guarantees that the statistical distribution of the data is the same between the training and the operational life. This means that if we are able to train a model on some data, then this model will behave similarly during the operational life. So we'll provide similar accuracy and performance. But as we know, this is not true in real working conditions because the stationarity hypothesis rarely holds. This means that we have to resort on adaptation. Adaptation is the game changer, and we have to integrate our tiny machine learning solution into the adaptation field. How can we adapt? This is a question that appeared even in questions or even in points present in the previous talks. We can deal with adaptation from two different perspectives: when to adapt and what to do when we have to adapt. When to adapt means that we can continuously adapting, as in passive solution, regardless of the fact that we have a change or not in the data. While in active solutions, we integrate our adaptation with a change detection mechanism, which is able to identify changes in the statistical distribution of the data. And we update our models only if we detect that there is a change. But then we have to decide, we have to deal with the change by means of an adaptation, which are the three main families of solutions that deal with the adaptation. We have instance selection, which refers to the fact that we have in our knowledge base, in our buffer, all the data acquired from time 0 to time t, where we detect that there is a change. With instance selection, we want to discard some of the data. We identify obsolete data, we remove them from the knowledge base, and we adapt our model only in the new data, only in the up-to-date data. Differently, in instance weighting, we don't remove knowledge, we don't remove samples, we keep all of them in our knowledge base, we just consider them with different weights. Typically, we provide or we characterize the most recent samples with higher weights. And finally, we have the family that refers to multiple models, where once we detect that there is a change, we not discard the knowledge, we do not consider different weights, but we just create a new model following the ensemble of model approaches. But if we consider the technological constraints on, as I said, the memory, computation, and energy, typically the adaptation refers to instance selection, because instance weighting in multiple models requires to have many models, and they require also to keep all the data acquired from time 0 to the time that the change has been detected. So we focus on instance selection, and I will deepen briefly the active and passive solutions. Well, passive refers to the fact that we have some data which are acquired by means of sensors. These data are processed for by the envisaged tinyML applications. And in the meanwhile, we continuously adapt our models following, it's some sort of online learning approaches. Differently, in the active approach, we have some data which are acquired by means of sensors. So these data processed by the applications. And in the meanwhile, the data are analyzed by change detection mechanisms, which are statistical techniques able to sequentially analyze data in order to detect changes. And then if a change is detected, the adaptation is triggered. I would like to quickly describe the just-in-time adaptive framework that we developed that refers to some data which are acquired from the environment by means of some sensors. The data are processed by an application, a given machine learning-based applications. We extract some features that could be statistical features or features coming from some filters. We have a concept drift detection mechanism, as I said, a change detection test. We have adaptation techniques. We rely on an initial training sequence, which is assumed to be change-free. We learn our reference concept that represents the concept after which we inspect variations about that. Then during the operational life, we keep on acquiring and analyzing these features. Once we detected that there is a change, we trigger the adaptation phase. We then go back to our data just to, not just to detect that a change has been raised, but also to understand the type of change, the magnitude of the change, as well as when the change started. So we go back in time to understand when the change started, because this is a crucial information then to support the next adaptation phase. Because all the samples acquired from when the change started up to when the change has been detected represent the new state of the process. So they represent the knowledge which are very valuable to train our new nodes, to update our reference concept. And if we have enough memory, then we can also consider to keep a library of concept such that we are also able to reactivate the concept if needed, some sort of recurring concepts. Okay, this describes the learning in presence of concept drift, but then we have to move these algorithms to tiny devices. So we have to consider efficient on-device learning. Here we have designed an algorithm which has been specifically focused for on-device tinyML for concept drift, translating the typical architecture where we have inference into the algorithm, where we can adapt our model not just over time, but in responses to concept drift. These models comprises 4 different steps, starting from the feature extractor, which extracts some features from the input XT. This feature extractor could be a pre-trained deep learning model that could be obviously based on transfer learning. It could be approximated by means of task dropping, so pruning and precision scaling, hence quantization. Then we have the dimensionality reduction, where we can reduce the dimensionality of the extracted features by considering a filter selection mechanism as well as autoencoder potentially. And then, different from other solutions present in the literature, we focus on a very simple and very effective statistical classifiers, which is the KNN classifier, which is a statistical classifier that operates as follows. It assigns the classes to an input sample by looking at the majority voting among the k nearest neighbor of the input samples. The main advantage of this classifier is the fact that it does not require a proper training phase. So we don't have to activate back propagation for training. We just put a new sample in the knowledge base, so in our buffer. The cons of this solution is the fact that the memory demand and the computational complexity scales with the amount of samples which are present in the knowledge base, so in our buffer. So the first step that we had to address was exactly this issue, and that's the reason why we designed at first a condensing algorithm for KNN, whose goal was to identify the smallest subset of training data that can correctly classify all the training samples. So we were able to remove some samples from the knowledge base while guaranteeing the accuracy, hence so reducing the memory demand and the computational complexity. But then we have the adaptation model, which is the core of our solution. So the adaptation models receive the input, has input the sample X and the prediction of the KNN Y. And when supervised information YT is available, we update the knowledge base of the KNN. How? We considered 3 different solutions exactly in line with the families of solutions that I just described for the learning in presence of concept drift. We have the passive update, where the adaptation is carried out at each new supervised sample. We have the active update, where the adaptation is triggered by a change detection test. And then we have the hybrid update, where we integrate the hybrid and passive and active. I will quickly describe them in few details, starting from the passive update. Let me recall you that the KNN classifier operates as follows. The adaptation is just done by adding 1 more samples in the knowledge base. But this, if we continuously add samples, then we will have problem of memory and computation. So we extended the condensing algorithm to a condensing-in-time algorithm. So the algorithm is able to understand over time if the new sample, the new supervised sample, is providing relevant information to the KNN classifier by considering if it has been correctly classified or not by the classifier. But then we had also to put a cap, so a maximum value in our knowledge base. And if we fill our buffer, then we have to decide how to remove some of the samples which are present in our buffer. And here we have two strategies. At first, a first in, first out, so a FIFO. But a more precise solution is associated to the fact that we can use different probabilities of replacing some of the samples which are present in the buffer by evaluating the variations of the classification error. Because if the classification error varies, in particular, if the classification error increases over time, this means that we are facing a construct drift, and this means that we have to quickly adapt our knowledge base over time. So removing in a faster the data which are present in our knowledge base. But differently, if our classification error is becoming more and more stable, we can decide to not to update frequently our classifier. This is the passive approach. Then in the active approach, we have a classifier, which is endowed with a change detection test. A change detection test is a statistical technique that is able to sequentially analyze data over time. Here we extended a well-known and widely used CUSUM test, the cumulative sum test. We extended by considering a multidimensional CUSUM operating on the classification error of our classifier, and we endowed it with a procedure to estimate also the time instant the change started. So we do not just want to detect that a change occurred, but we want to understand when the change started once it has been detected. And we could do that, we did that directly on the formalization of the multidimensional CUSUM. And then we integrated the passive and active, because in this way we are able to continuously adapt our model by considering the condensing in time. And we had also the ability to detect changes by analyzing the statistical distribution of the data by using our change detection test. So if a change has been detected, we then operate on the knowledge base that trained by the condensing in time algorithm to remove the obsolete knowledge. I would like to quickly describe some results just to provide you three highlights. These results refer to the speech command identification applications, but we have very similar results even to the image recognition. The three main highlights, the three main points I want to highlight refers to the fact that at first we compared the hybrid, the active, and the condensing in time, so the passive approaches to state-of-the-art solutions in the field of learning and presence concept like Adwin and SAM. And we had higher performance or higher classification accuracy by considering a technologically constrained devices. So by putting a cap on the maximum amount of data which are able to be managed by the device. The second point I want to highlight is the fact that if you see on the picture, you see the vertical red lines that represent when the concept drift is present, and the concept drift here refers to the introduction of noise, distortion, reverb, and echoes. And as expected, once we have a concept drift, we have decrease in the classification error, decreasing classification accuracy of our solutions. But then our models are able to quickly adapt to new working conditions and quickly recover the classification abilities they have. And finally, we implemented the hybrid tinyKNN on off-the-shelf boards, which are the STM32 boards, the H7, the F7, and the F4. And here you see the technological details. We implemented our hybrid tinyKNN, and here you can see the execution times in milliseconds. For the three main steps, the computation of the spectrogram, the feature extraction, and the classification with the 10 and 50 samples. And what you can see here is the fact that our main concern was associated to the memory and computation, in particular the computational demand of the KNN classifier. And here you can see that the execution times of the KNN, both on 10 and 50 samples, is well below the execution times of the spectrum processing and the feature extraction. So we can resort on this algorithm for the execution of the speech command. I would like to conclude with two current research directions that we are considering. The first one refers to semi-supervised tiny machine learning, in particular semi-supervised on-device tiny machine learning, because we want to consider, we are considering all these scenarios where the supervised information is scarce, is expensive, or it might come from, say, in an imbalanced way only on, for example, in given classes. And the second research direction that we are currently pursuing is the design, the development and deployment in an automatic way of online tiny machine learning. So we are designing a toolbox which is able to automatically translate a static traditional machine learning solution, deep learning solution, in particular tiny machine learning solutions based on TensorFlow Lite for micro into a on-device training tinyML. Thank you, Danilo.
Thank you, Manuel, for your great talk. There is a space for a couple of questions. Since I don't see them on the chat, I will pose a couple for you. The first, how, if applicable, how do you make sure or characterize quantitatively that overfit will not affect the learning process given the few amount of samples that the techniques you explained uses?
Yeah, that's a good point. Thanks to the type of classifier that we are using, our goal is to identify the correct value of K in our KNN classifier. So we designed a theoretically grounded solution that is able to automatically define K with respect to the amount of data that we have, because we don't have backpropagation to actuate, and this is an advantage from this point of view. We have problem of overfitting once we have to identify the reference concept of even for our change detection test, because again, we have to train it, we have to estimate the characteristics, the features of our change detection test. And I would say this is an issue that we have to deal with. We addressed it by considering separately training and validation. So we are considering both training and validation on the amount of data that we have, which is say quite straightforward solution, but this is an issue in during the operational life, because if you detect that there is a change and you are able to quickly detect it during the operational life, you might have very few samples from when the change has been detected and when the change started. So you have very few samples to retrain your model and to retrain your change detection test. And in this particularly critical solutions, what you have to do is that you have to start in an emergency situation, your classifier, wait for a few more samples, I don't know, 50, 100 samples, and then you retrain your model. But in the meanwhile, one could say, okay, but you might have even a further change in those data, which is true. So before retraining in your model, while you waited for a few more samples, you can resort on statistical solutions like change point methods that allows you to evaluate whether you have changes on a given subsequence of data. So before retraining your model, you check if there is no change there, because if there is no change there, okay, you can retrain it. If there is a change, okay, you have to wait, continuously operating in emergency mode, and this emergency mode means that you are considering a very light classifier and very light change detection test.
Thank you so much. There are 3 questions in the chat. The first, where do I find more information of your research on self-supervised tinyML?
We are currently working on that. You can contact me directly, and I can pinpoint all the activities that we are currently working on that.
Maybe Manuel, you can type an answer about how you can be contacted, so that
the email that at the beginning I said there is my email. I could put my email in on chat.
Thank you.
Okay.
The second is how do you prevent a catastrophic forgetting in your framework?
That's a very, very good question again. Here, the catastrophic forgetting is typically associated to the fact that we are continuously, or we are learning say, very good only the last few samples, and we are forgetting the previous samples. Here, the point in our particular framework where we have a KNN with instance selection, the point is that we have to understand very well which is the point, say, where the change started in time. Because in that point on, we could say, okay, we can discard all the previously acquired samples. We focus only on the samples that represent the new state of the process. And in this case, we can mitigate the catastrophic forgetting. And then one could ask, how can I be very effective in estimating the time instant the change started? Again, we resort on statistical techniques like the change point methods that allows us to make two relevant things. The first thing is to perform a further level of analysis of the data in order to remove false alarms. Because we mentioned catastrophic forgetting, but then false alarms is another relevant problem, because in false alarms, we are wrongly removing knowledge. So the change point allows us to remove false alarms and as well as provide a very accurate estimate of the time instant the change started.
Thank you. And last question. I think you mentioned that you also had good results on different tasks, image-based, etc. Can you comment on what you explored and what you needed to tweak in your algorithm for different domains?
Okay, we have expertise so we made experiments, and we had expertises in audio, speech recognition, images, and even MEMS accelerometer data, as well as radar data. The main issue there is the fact that you have to carefully select the feature extraction phase. Because you can obviously use a transfer learning from image to image task, but it's rather difficult than to make transfer learning from audio to images. What we can do is the fact that we can understand, we can create say good models by relying on all the information we have, and then we endow with our on-device tiny machine learning with the feature extraction that at best represent the application that is going to be addressed by the envisaged tinyML application.
Thanks again, Manuel, for your great presentation, and to follow up with the question from attendees. Thanks, the strategic partners, once again, because without them, these type of forum and many other initiatives would be impossible to organize. And the strategic partners are ARM, very quickly, Edge Impulse, Qualcomm. Then we have the Platinum strategic partner, DeepLight, Clicatech, Reality AI, Renesas, Sony Semiconductor, the Gold strategic partner, Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SensiML, STMicro, Synaptics, ScienceSense, and then a bunch of silver strategic partners, which are listed here. Thanks a lot. It was really a great afternoon for me, and whatever is your time zone. Thanks a lot. No words to express gratitude to the professors and all to attendees for being patient for the extra time. Thank you, and see you tomorrow. Have a nice day or evening. Bye.